So this is what you have to implement in a code, right? So this is what I have here. I've opened it up here. I have a whole bunch of, files here. This one is written in Fortran, but you should be able to read it quite easily because Fortran and MATLAB are very similar. So forget about all this stuff. This is like, specific to Fortran. All right, then what I've done here is, can everybody read the font or is it too small? Font size okay? All right. I've opened two files here to print out stuff, okay? And again, you may not need that in MATLAB, but here what I've done is I've opened one file here, which is basically for printing out all my data for contour plotting, and here I have printed out a file which is for the residuals, okay? Here's my mesh calculation. You can see here, again, notice that I'm not using 1 here or some number here. I have a length which I've defined somewhere else, and I'm using that length and the number of points I've prescribed nx and ny, okay, in each direction. And I'm calculating dx and dy. Again, keep these flexible. Notice also that what I've done here is I've calculated an aspect ratio, which I'm calling AR, which is dx over dy, because that shows up in my equation again and again. Every equation you look at, there's a dx over dy or a dy over dx. Okay, that's what you get from your finite volume formulation. So you don't want to repeat that calculation on the fly again and again. You're wasting multiplications. Okay, because in this case you have uniform grid spacing, so why not store that ratio? So here I have dx over dy, and here I have this one I'm calling RA, which is basically inverse of that, dy over dx. Okay. All right, then my rho and gamma, again, these are defined as two-dimensional arrays, all right, and I've kept them general so that later on I can use them as variables, but all I'm doing is I'm filling them up with the prescribed values of density and viscosity that I have from the homework write-up, okay? So basically just filling up everything with those numbers, but they're defined as variables, okay? Then I'm initializing my arrays. Now, by the way, this actually means that if it's defined as an array, then this actually means this. Okay, even though it's not explicitly stated, or this comma. That's what it means. That the full u velocity. So I'm calling it uu instead of u. The full u velocity is initialized to 0. V velocity is initialized to 0. Pressure, as you know, this is gauge pressure, is initialized to 0. Okay. After I've initialized everything, now I realize that, well, some of these actually also include boundary nodes, because remember, in a staggered mesh, these are not just interior cells we are looking at. Okay. In the picture that I had drawn a little while ago, here. Oops. Here, you can see that here I have U nodes. Here I have U nodes and so on. Okay. Similarly, here I have V nodes. Here I have V nodes. So some of those, so my U and V, maybe I should go back and show you the data structure once, because that's very, very important. So this is, let me just go over this before I go over the main code. So these are just, this is a program which specifies all the parameters I need in the code. So for example, I'm saying momentum equations, I'm going to iterate, do 2 sweeps of ADI, okay? Pressure correction, I'm going to do 40 sweeps, okay? Total number of iterations, I'm setting a maximum limit to 2000. So basically I'm saying if it exceeds 2000, then just stop anyway, okay? So that it doesn't go into an infinite loop. Here is my relaxation. This is your omega UV, okay, 0.8. Here's your relaxation for pressure, omega p, okay, 0.2. Here is my inner iteration tolerance, although I don't think I use this. But in case you use this, instead of using number of sweeps, if you said, okay, I'm going to set a tolerance criterion, I'm using 3 orders of magnitude, okay? Here is my outer iteration tolerance criterion. So I'm saying all my conservation equations should converge to 10 to the power minus 10, absolute value, okay? Here is my inertial damping factor, 0.2. So this RIN is the relaxation, inertial relaxation for U and V, okay? So these are all set up on top. Then, like I said, this is your grid spacing. This is your length, okay, 1 centimeter. And then I have the dimensions you can see for XC and YC. These are cell centers, okay. You don't need to make them two-dimensional because, you know, for a given Y, the X values change only, 40 times. It doesn't change 40 times 40 because it's a square mesh, okay. So I made it, one-dimensional instead of two-dimensional. Here's your U lid. So I have a comment here saying that 0.1 meters per second actually gives Reynolds number of 1,000. So that is just for my own reference, because when I change it, I know exactly what the Reynolds number will become. Okay. And then here you can see these are the actual data structures for each of the variables. All my scalars, gamma, pressure correction, they are dimensioned n times m, okay, or nx times ny. U velocity, V velocity, and density, they are dimensioned nx plus 1 times ny plus 1. Why? Because I have that extra node on the boundary for U. Okay, actually, I mean, U could be dimensioned nx plus 1 times ny. That's the actual dimension, but I just made it one extra slot. Okay, actually, rho can also be dimensioned here, nx and y. Should probably put it there. The extra slot is never used. And then you have your link coefficients. This is your x coefficient link coefficients. Notice that again, they are dimensioned nx times ny. Okay. So for each cell, I have a link coefficient, and there are 5 of them. Similarly, for the y momentum, I have 5 link coefficients. Okay. And then finally, these are my boundary velocities. They're one-dimensional, as you can see. For U left, right, V left, right, I have times ny, and then for top and bottom, it's times nx. Okay, and then these are just single scalar numbers that I've defined. So this is kind of the data structure that I was talking about, that you need to set appropriate dimensions for your U and V velocities. Okay. Any questions so far? All right. So so let's go back to this other one here. So that's what we are doing here. We are setting everything to 0 first, and then we are rewriting on top of that the boundary conditions. So for example, the very first row of U velocities here, so these all have values of 0. Okay. Similarly, these all will have values of 0. Okay. These all, well, they are not. There are no nodes there, but the V velocities there will be 0, and so on. So that's what we are doing here. Setting my nodal values appropriately, as well as now setting my boundary conditions. So I'm saying the left velocities are all 0, the right velocities are all 0, but the top velocity is equal to U lid. Okay. So this is the main program, and then in the main program there is nothing else. There is just a huge loop. This is your outer iteration loop. Okay. And this follows exactly what we had here. Okay, so this is this big loop here, and as you can see, it exactly follows what you have there. You're calculating link coefficients, x and y momentum. You have to do it separately because the interpolations are different, remember, for a staggered mesh. Okay, so that's why you cannot combine them. And then you solve your x momentum, solve your y momentum, solve your pressure correction. Now, ideally, you could have another procedure here which calculates the link coefficients and the sources for the pressure equation, but I have done it inside this all itself. And then you correct your velocity, correct your pressure, and then you write out whatever stuff, and right here you check for convergence. So that is exactly what we have here. You calculate links, solve x, solve y, solve pressure correction, correct velocity and pressure, check for convergence. Okay, so one-to-one relationship between what I have there in the algorithm and what I have here. Okay, now again, this is something, you know, you can do it various ways. So what I do, for example, is, of course, these residuals, res u, res v, res p, are the R2 values of u, v, and p that we calculate, okay, right here in this algorithm, these three, okay. Those are calculated somewhere inside these and stored. And then here, I simply print them out on screen so that when I'm running the code, I can see on screen whether it's converging or diverging. I also write it out to a file so that I can plot it out later. Okay. Now, there are many ways of doing this. You know, sometimes I see students, they make up a vector which stores the residual at different iterations. That's one way of doing it, but to me, a better way of doing it is simply writing it out to a file. Because that way you're not using compute time or random access memory, RAM. Because anytime you store the residual vector, it is keeping on growing, right? Sometimes your code, if you're solving a complex problem, it may take 10,000 iterations or even more. Okay, and you're storing all those numbers. Why store all those numbers? Why just not write it out to your hard disk? Okay, so that's again, you know, your choice how you want to do it. But I, or all commercial codes usually do this. They would just write it out to a file and that's it. They would not store it in memory. Okay. And then what you're doing is, so they would only store the current value in memory, just these three numbers. That's it, not the whole vector as a function of iterations. All right. And then, and also, you know, another thing to think about there is if you're doing transient calculations, then you would have these for every time step. Okay, it's a lot of data that you would have to store. But if you write it out to a file, you don't have to worry about all that. And then you can take the file and plot it. Okay. And then this is where we are checking for convergence, which is very straightforward. It's saying that if the residual is less than the tolerance for all three variables, then you exit. Exit is like break in MATLAB. You just go out of the loop. Okay. And then once you have exited, this is where you do all your post-processing. For me, I use TechPlot, so I've written out everything in TechPlot format. But for you, you know, you use whatever plot commands you have in MATLAB to plot your data. And this is where you may do some acrobatics with your array size and shape before you plot your contours. Okay. So that's the main structure of the program. So, you know, if you think about it, this is how you need to think about it. And now you say, okay, what's going to go into this first function that I write? Okay, so that first function is simply calculating link coefficients. So I'll show you what it is doing. You can see here I have something called link x momentum. Okay, and this is pretty straightforward. All it is doing is calculating your link coefficients based on, I don't think we have it here in this equation, in this lecture. Let's go back to lecture 9 here. So if you go back to lecture 9, there we go. This is exactly what I'm coding in. Okay, so I'll just kind of show you an example here. So we'll keep these side by side. Can you still read the font from behind? Okay. So you see what I'm doing here is to calculate this, for example, A East. Okay, let me just go down here. So here's my A East, right here. This is what I finally calculated, okay? So to calculate this guy, I need first my rho East. I also need my mu East, okay? And that is what I've done here. So for example, my rho East is rho naught. This is again based on the staggered mesh interpolation formulas that we had. You see 2 of them are direct relationships and 2 of them are 4-point relationships right here, divided by 4. Okay, that's the 0.25 multiplication there. Okay, so that's what it is doing. It's interpolating the rho, calculating rho east, rho west, rho north, rho south. Okay, and then it is calculating the C east, C west, C north, C south, which is nothing but basically these guys. Rho times U is what I'm calling C. Okay, some people use it for convective link, but that's what that is. Okay, because we can't use AE we are using for something else, so that's why they call it CE. Okay, so the CE, C west, C north, C south is nothing but basically your these guys, okay, computed the rho east, rho times U or rho times V computed appropriately. Again, this may use, you know, remember you had that northwest plus north type of formulas, and that's what you see here. Some of these are, you know, as you can see, there's I minus 1, J plus 1. Okay, that's a northwest node because J plus 1 is north. I minus 1 from there is northwest. So it's doing a summation of north and northwest. That's the northern faced rho times Vn, rho n times Vn. Okay, so that's what this is doing. And then for gamma, again, same thing. You use the same interpolation as you did for rho. Okay, and then finally you have these formulas, and if you look at this one here, this is exactly what I have right here. Okay, negative half of absolute value of CE, which is right there, minus CE, which is right there, okay, times dy, which is right there, minus dE, which is the mu E basically, times RA. RA is delta y over delta x. AR is delta x over delta y, RA is delta y over delta x. Okay, so the reason I'm showing you this is keep your code clean. If you write it this way, you will be able to debug your mistakes easily, because there's a one-to-one correspondence between what you have in the code and what you have on paper. Okay, if you write your code differently from what's on paper, you will find it difficult to debug down the road if there is a mistake. So this is an example of calculating the link coefficients of the x momentum equation. And now if you look at, you know, your loops, you see here what I'm doing here is I'm going from 2 to nx. Okay, so if I go back to this figure here that I had, okay, so I'm going from this here to this last node here in the x direction, and in the y direction though I'm going again from 2 to ny minus 1. I'm not going the last row and the first row. Why? Because they need special treatment for boundary conditions. Okay, because those equations are different. These equations that I just showed you here, they are applicable only to interior nodes. They are not applicable to boundary nodes. That's why I'm going from 2 to ny minus 1. For 1 and ny, I have a special treatment. That's what you see here, bottom wall. Okay. Again, you go back and look at your equations. There is an exact one-to-one correspondence. Notice that for the bottom wall, the southern link coefficient is 0. Okay. And everything else has been modified accordingly. You see here there are these, you're familiar with this 3 ds times AR, and then there's a 8 somewhere, but the 8 of course has fallen out because the velocities are but it should show up here, right there. There is that, then there is that, and I'm looking for the 8 somewhere. Maybe it's, I guess it's, those are the 2 ones that we have, okay? So, but that follows directly from your special treatment of the diffusion term at the boundaries. Okay, you get an extra term in the source and then an extra term here in the diagonal. All right, or sorry, in the northern and in the diagonal. Oh, okay, the other term is in the source. Okay, now the source I've calculated elsewhere. I'll show you later on. That 8 term is actually in the source. That's what I was confusing me. But you see, so here's bottom wall, and then similarly we have top wall, j equal to ny. Okay. So special treatment for boundary conditions. This is the main loop for interior nodes or interior volumes. So this is your x momentum link. If you look at your y momentum, it will be identical. Okay, very similar. All right. So those are the 2 link coefficients. Then we get to solve. This is where your ADI solver is. And remember, we're solving the equations in correction form. Okay? We're not solving them in the original form anymore. So let's look at that a little bit. So you can see here, this is solving the x momentum equation. Okay. So first thing, remember we said if I look at our algorithm, so remember we are calculating these. Remember we said residual for the momentum we are going to calculate and store right before we do even any sweeps. Okay. So that's exactly what I'm doing here. I'm calculating the residual right away. So I'm starting my iteration loop. This is my inner iteration loop. And I'm saying if the iteration number is 1, which means that I have not done any sweeps so far, I'm going to store that residual. Okay, so when this number is 1, the very first time I enter, I'm going to store that residual. I'm calculating it for all cases, but I'm only storing it if iteration is equal to 1, because that's what I'm going to monitor. Okay. Now, what is the residual? Well, the residual, you can see it's pretty straightforward. I've taken all the equations. So this is A naught times U naught, A west times U west, and so on, minus, your source term for pressure, squared and added. That's all it is. And then finally taken a square root. Okay. So that's your residual. Then you get to your sweeps. So this is where your ADI starts. Now, you're all familiar with this. I just want to point out a couple of things. Okay. So let's say we are starting at j equal to 1. So this is the bottommost row of x momentum nodes, u velocity. Okay. Now, here is what's going on. Let me see if I can draw a picture here. Hopefully I can. Yeah, good. Let me use black. Here is my computational domain. All right. And I'm just going to draw maybe a 4x4 mesh. My u velocities are right here. And here. So if you really look at this, so notice that my j is equal to 1. I'm on the first row, okay? If you really look at this, I don't need to solve for that guy and that guy. My only unknowns are really these 3, okay? So if I set up a tridiagonal solver, it should actually be my total number of nodes. This is 1, 2, 3, and so on, and this is nx plus 1 at last one. Okay, Because you see there are 4 cells, so my nx is 4. This is 5th one, nx plus 1. Okay? So number 1 and nx plus 1 I don't need to solve for. I need to solve for 2 through nx. That's my solution domain. So when I set up my tridiagonal solver, it should be set up for that many equations. That's actually nx minus 1 equations, right? So now if you think about this, if let's say this is my u2, u2 actually becomes in my tridiagonal solver my first unknown, phi1, and then unx becomes my phi nx minus 1. So this is my general unknown number, and this is my actually corresponding u velocity that I'm solving for. So the first unknown that I solve for is actually u2, okay? And the last unknown that I solve for is actually unx. So you have to understand that when you're setting up your tridiagonal solver, because you're not setting it up from 1 to nx plus 1. I mean, you could do it if you wanted to do it that way, okay? But that's not how I'm doing it here. I'm setting it up from 2 through nx minus nx, okay? So here is what I'm doing. I'm saying, okay, my first unknown is I equal to 2, okay? I'm creating a local index, which is I minus 1. So if this is my u2, that actually becomes my unknown 1, okay? If this is my unx, that actually becomes my unknown nx minus 1. So this IL is a local index that I'm using only for my tridiagonal solver, okay? So that's what I'm doing here. There's a transformation of index, and then I'm saying, okay, my diagonal with that index, so D1, for example, would be that. Now notice that what I'm doing here is I'm taking the diagonal that I've already calculated, I'm multiplying it by 1 plus omega, or 1 plus alpha, which is your inertial damping factor. Okay? And then my C becomes my A east, and then obviously for the very first one, there is no west, okay? Because the west times the boundary condition that has already moved over to source. So there is no western coefficient, all right? And then this B, okay, so here is my right-hand side now. Right-hand side has pressure source, okay? The difference between two pressures times dy. I've transposed the northern coefficient because I'm setting up a row-wise tridiagonal solve. So the northern coefficient is, the northern term is treated explicitly. So that has been transposed over to the right-hand side. And then there are contributions from boundary conditions. And this is what I was talking about, this 8/3 that comes from the bottom boundary. Okay. And then because this is a corner node I'm looking at right here, there is also this contribution which came over from this node. Because this guy is going to have a contribution from that bottom boundary as well as from this left node. So this is the left node, this is the bottom boundary. Okay? Everybody follow this? Okay, so this is where I would normally stop if I had the equation in its original form, without the correction form. But now I'm saying I'm going to do it in the correction form. In the correction form, my right-hand side actually has the residual itself. So what am I doing here? I'm saying, okay, whatever right-hand side I calculated, I'm also going to subtract out the rest of the equation from that. Okay, so the idea is my residual is my source minus A naught phi naught minus A east phi east minus A west phi west. Well, let's forget the west for this case because there is no western node. So that would be my original residual. So what I've done in the first step here, right here, is I've only, oops, sorry. is that I've only calculated this part, okay? And then in the second step here, I've subtracted out those two. That's this line there. So the first, if I stopped after the first step, then that would indicate that I have coded in actually the original form of the equation. If I now add the second step, this step right here, then that means I've changed it to correction form. Because instead of using the right-hand side as it would correspond to the original form of the equations, I'm now constructing the residual. Everybody clear on that? So these two terms have also been subtracted out from here. Okay? And then you go for the rest, which is this node, and, well, in this case, it would be only that node, number 3. Okay? And then the last one, which is that one, NX. Again, you need boundary conditions there, special treatment. Okay? And then I call my tridiagonal solver right there. So this is my TDMA. Notice that the total number of equations is nx minus 1 that I'm solving for. Once I've solved it, here is what I'm doing. I'm saying my solution, okay, so my solution, this solution, according to your notes, is called U tilde. Okay? This solution, what I'm saying is whatever solution I had, I'm adding that update. Now notice that this index is different from this index because it's displaced by 1. As I said, number 2 is the first unknown. Okay, so if you think I is equal to 2, it's saying U2 is equal to U2 plus phi of 1. Okay? Everybody understand that? What's going on here? So that's the update step. And then, you continue with that. Next, you do the interior rows. Same idea. You will have different terms and so on. Let me just wipe this out so it's easy to see. I mean, the interior nodes, it's pretty straightforward. You see you have a diagonal here, right there. Right there, I have a diagonal. Okay, here is my eastern coefficient, western coefficient, and then again, the right-hand side has the pressure source, the northern coefficient, and the southern coefficient. That's the standard ADI form, okay, because now we are in an interior row, okay. And then to convert it to correction form, I also took out the eastern, western, and the north, the 3 terms. So I already had south and north on the right-hand side. Now I've also taken out the east, west, and north, which means I've actually constructed the residual. Okay? So this is your ADI sweep, and then we go to top row, same idea, and then we start with the column-wise sweep. Okay? You can figure this out for yourself. It's the same equations, just written differently. So those are the, that's your solution of the momentum equations. Okay, now here I have at the very top, I'm saying right here, I'm sweeping that many number of iterations, and that number had been set to 2. If you recall, okay. Now, the way I'm counting it is I'm not counting row-wise sweep as 1 and then the column-wise sweep as 2. This is basically 2 sweeps of row plus column. That's what I'm doing. Essentially 4 sweeps. Okay? That's what we're doing here. So that's the X momentum solver. Any questions on that? So Y momentum solver will be very similar. I'm not going to go over that. Same idea. Okay, nothing changes. Let me just quickly, lastly, show you the pressure solver. Let me see if we can locate the pressure correction. Okay, there are your coefficients for the pressure equation. Okay, the source is the mass imbalance, as you know. So if we go to the pressure solver, okay, so here you can see straight away, this is where my mass imbalance calculation is, m dot. Okay, simply rho u east minus rho u west divided times delta y plus rho v north minus rho v south times delta x. Pretty straightforward. Okay, these are the velocities I calculated in the x momentum equation. I'm just bringing them in and calculating. Okay, and then what I'm doing here is I'm constructing the residual. Now, as I said, you may or may not include the pressure correction in the residual calculation. You can simply do the L2 norm of that. That's fine. Okay, but I have included the pressure also. You can see the m dot is here, but the pressure corrections are also there. And then again, first iteration, I'm storing it. Okay, that's what I'm going to monitor. Then I go into my row wise sweep. This is very straightforward. You can see here is my m dot I'm calculating. Okay, and then my let's just go to some interior row here. Here's my m dot. Here's my diagonal. Okay. Notice it's using link coefficients of the momentum equation right there. That is exactly what you have here. Okay. It's using these link coefficients in the denominator, as you can see. Okay. That's what you have here. And then here is your eastern coefficient, western coefficient, and then right-hand side has the mass flow rate, and then of course you've transposed over, in this case, because it's the bottom row you're looking at, you've transposed over the northern term to the right-hand side. Okay. Same idea, and then you solve your tridiagonal solver, and then you're simply saying my PP is pressure correction in this case, is equal to whatever my solution is. Okay. In this case, there is no index shifting or anything like that, because the green dots are exactly like you would have in a collocated mesh, nx times ny. All right. Same idea. You do interior row, top row, and then you start with your column-wise sweep. So by the time you reach the end of this this iteration loop, basically you will have solved for your pressure correction. Okay. And again, the number of iterations we are doing here is that number right there, okay, which has been set to 40, as I showed you. Those are the number of sweeps. So I'm not really monitoring the residual in this case. I'm just going by the number of sweeps. Even though I'm calculating the residual here, I'm not monitoring it. Okay. All right. So that's your pressure solver, including calculation of the link coefficients. And then finally, if you look at here, after you solve this, all you need to do is correct your pressure and velocities. Okay, and that's pretty straightforward. It's a very simple code right here. Pressure correction really has nothing. You will see one line. Okay, this somehow got messed up. Let's see. Okay, there we go. You can see there is really nothing. It's just says pressure is equal to pressure plus relaxation P times PP. Okay, it's a full field vector operation. It does it for all the nodes essentially. This basically means pressure within parentheses colon comma colon. Okay, all I and j nodes. That's what it is doing. But that's all there is to it for pressure correction. Nothing really, which is, you know, as you saw in your algorithm, after you've done all this, that's all you need to do. Okay, right there, this step. Okay, and then velocity, same thing. You do these steps here. Okay, so that is equal to that. you need to use your pressure corrections. Okay, and so that is what you will see here. If I look at UV correct, there should be something called that. Here it is. Messed up. Sorry about the font. I know it's difficult to read. Let's see. Yeah. So that's all this is doing. You can see I'm simply taking the velocity right there. Okay. And then relaxation of the pressure, the difference in pressure corrections divided by the diagonal, which is essentially this formula right here. Okay. So this velocity is what my momentum equation calculated. This pressure correction is what my pressure correction equation calculated. And I'm simply using the two, including the link coefficients, which was calculated way up on top. Haven't changed that yet. Okay. And using that formula. And the same thing for V velocity. And that's it. You're done with your U and V corrections. Okay. And so we get to the very end. You've done all that. Now you monitor your residual and you exit. Okay. So this is the general structure.